8 billion tons is the weight of plastic waste, turning the oceans into a giant dumping ground. One can notice how the water carries synthetic traces rather than just salt. Engineers in the United States refuse to stand by. They developed an intelligent system to intercept this pollution. But this is just the beginning. Why utilize the power of natural ocean currents? Artificial propulsion is inefficient for such vast areas. This design allows marine debris to drift into a capture zone on its own. Other nations hesitated, but American specialists launched the mechanism. At first glance, the barrier seems static, but in reality, it adapts to the open sea. It is visible how the machine guides trash into the hold. Nothing is predictable in these waters, yet the system holds firm. It gets more complex further on. The waste is trapped, awaiting the next stage. 20 million tons of debris plunge into the ocean currents every single year. One can notice how the majority of this influx consists of plastic, a material resilient enough to withstand the corrosive environment. Why does this specific composition pose such a persistent threat? It seems like the waste might simply disperse over time, but nearly 80% of this volume remains intact, enduring underwater for centuries. The process is only gaining momentum. Fragments accumulate into enormous floating garbage zones, visible as dense patches on the water. At first glance, this looks like static surface pollution, but in reality, the material quietly seeps into the marine food web. It harms more than 700 ocean species, eventually impacting humans. According to environmental organizations, proper retrieval changes the equation significantly. Waste transforms into valuable resources, from repurposed plastics and engineered fibers for the textile sector to reclaimed metals. The recovery process saves thousands of kilowatt hours of energy and prevents millions of tons of carbon dioxide emissions. It does not end at this stage. Discarded materials find a new life within the circular ocean economy. Two hydraulic mechanical arms extend outward to sweep across the water in a broad, fan-like pattern. Gathering such vast volumes of debris in the unforgiving conditions of open waters requires nations to deploy highly specialized technological systems. In major accumulation areas, such as the North Pacific Gyre or the Gulf of Thailand, dedicated cleanup vessels serve as the primary workhorses. One can notice how the arms capture drifting refuse ranging from plastic bottles and discarded bags to derelict fishing nets. The collected material is directed into floating channel systems linked to the ship. But this is just the beginning. Stainless steel conveyors positioned on the deck receive the load and move it into large holding compartments. A single cleanup operation can run for 8 to 10 hours, gathering as much as 5 to 10 tons of mixed marine waste. Why do engineers deploy compact mechanical equipment in rivers instead of simple nets? It would seem that standard barriers could easily trap the flow of trash. But in reality, dense layers of waste build up in reservoirs and restrict water movement, requiring heavy force to extract. Clamshell excavators mounted on dump trucks lower steel buckets weighing close to 1,000 pounds deep below the surface. They scoop up mixed debris, including bottles, plastic bags, branches, and even old tires. Every single lift can remove between 500 and 1,000 pounds of trash. With the help of hydraulic power, one crew can clear a river segment hundreds of feet long within just a few hours. This makes the process nearly 10 times faster than manual cleanup. It gets more complex further on. Yet in many coastal regions, collection still depends on local fishermen and volunteers who use small nets and hooks from their boats under the scorching sun. Each individual may retrieve only a few hundred pounds of waste per day, but their effort represents the essential first step in the recycling chain. Trash skimmer vessels, specialized boats engineered solely for capturing floating debris, carry the collected waste back to shore. A compact skimmer measuring roughly 25 to 30 feet in length can accumulate around 5 tons of material during an 8-hour operation. When its storage area reaches capacity, a hydraulic conveyor at the bow lifts the entire load. One can notice how the machine discharges the mass into the receiving zone on land. The process is only gaining momentum. At first glance, the freshly offloaded mixture looks like chaotic refuse, but it is here that the preliminary sorting phase officially starts. The pile includes a wide spectrum of items: plastics, metals, wood, seaweed, and organic sludge. Workers conduct a rapid inspection to remove oversized or dangerous objects. Steel nets, oil buoys, and tires are pulled from the mass before they can damage the downstream equipment. Therefore, the remaining material is shoveled onto a feed conveyor that transports it into the screening system. Inside the sorting line, a trommel drum rotates ceaselessly to classify the waste by particle size. It is visible how sand, silt, shells, and tiny fragments pass through the perforations while bottles and packaging stay inside. And this is not the limit. This residual stream, which consists mainly of plastics and nylon, moves to a manual sorting belt. Workers separate each category in preparation for the next stage of recycling. 15 to 30 minutes is the duration the cleaning phase typically occupies, dictated strictly by how heavily the waste is polluted with marine contaminants. The detailed sorting process first separates materials like metal, glass, and wood, routing them to dedicated processing lines, while plastic begins its own distinct path toward renewal. Why is this step essential before any recycling can take place? Ocean debris typically spends long periods submerged in salt water, becoming covered with tenacious algae, oils, and microbial growth. Without thorough removal, these impurities would compromise the chemical integrity of the renewed material, rendering the entire extraction effort useless. Inside the processing zone, the material is fed into a mechanical wash tank, where rotating shafts equipped with paddles generate a turbulent flow. This aggressive motion scrapes off surface buildup and rinses away impurities, while the wash liquid utilizes gentle cleaning agents and a chloride neutralizing compound to eliminate salt and oil residues. One can notice how the water changes color as the grime detaches, especially when the temperature in some facilities rises to between 160 and 180 degrees Fahrenheit to boost sterilization. The wash materials then move into a drum washer, which spins while blasting them with high-pressure water streams to dislodge stubborn sand and algae. Afterward, a float sink tank classifies the plastics by density, where polyethylene terephthalate settles at the bottom, while high-density polyethylene and polypropylene remain afloat. This ensures that the separation is absolute before the material proceeds to the next phase of the cycle. Therefore, the freshly washed material must be transferred to a centrifugal dryer to extract remaining moisture, followed by hot air drying at roughly 170 degrees Fahrenheit. In larger plants, engineers install ozone-based deodorizing systems to treat vapor emissions, effectively removing organic smells and neutralizing bacteria. Once the collected plastic waste arrives at the facility, the first step in the recycling workflow is pre-sorting, dividing plastics by category and size. At first glance, this seems like a simple mechanical division, but in reality, it is a complex multi-stage filtration system designed to prioritize the two most efficiently recyclable plastics while rigorously excluding incompatible materials. The mixed plastic feed moves into a large rotating steel drum where small perforations allow dust, sand, and fine particles to drop out. Larger bottles continue moving forward, ensuring a coarse size classification that helps prevent blockages in subsequent equipment. Next, the stream travels along a manual sorting line where workers pull out unwanted items such as metal cans, nylon, and cardboard. Simultaneously, An automated cap and label remover uses vortex air pressure to strip away different plastic components. Magnetic detectors continuously scan the flow, ejecting any residual metal pieces or staples. But this is just the beginning. After this mechanical purification step, the remaining material consists primarily of clean, uniform bottles, now ready for the grinding phase. Hundreds of alloy blades spin at several thousand revolutions per minute inside the chamber of the high-speed granulator. They slice the bottle bodies into small pieces known as flakes, transforming what was once a mountain of bottles into a steady flow of uniform material. In a single hour, one machine can handle between 2,000 and 3,000 pounds of plastic. One can notice how the bulky containers disappear into the unit, emerging seconds later as fragments only a few inches in size. This grinding step not only reduces the material's bulk, but also enhances energy efficiency in later stages. Because the plastic is broken down into fragments, it melts more quickly inside the extrusion unit, cutting electricity use by up to 40% compared with melting solid plastic chunks. The granulation phase also acts as the first level of size control, ensuring the feedstock is consistent. From here, the process transitions to the microscopic scale, where optical systems take control. High-speed sensors examine each individual flake, assessing its color, clarity, and surface characteristics in just a few thousandths of a second. When the equipment detects a transparent fragment, a green piece, or an unrelated material such as wood or glass, a precisely aimed jet of compressed air removes it from the mainstream. A single unit is capable of handling more than 1,000 particles every second, maintaining an accuracy level exceeding 95%. Each air pulse is directed at only one tiny fragment, weighing less than 1,000th of an ounce, without disrupting the nearby material. The outcome is a flow of clean, uniform plastic flakes, sorted neatly into distinct categories, forming the essential base for the pelletizing stage. These approved flakes are delivered into a large-scale extrusion unit, where they are heated to roughly 520 degrees Fahrenheit. At this temperature, the plastic liquefies and moves forward along a massive rotating screw. As the pressure builds, the molten material is forced through an ultrafine metal screen that captures any lingering contaminants. The refined plastic melt is then directed into an underwater pelletizing system, where it is instantly chopped into millions of tiny granules known as pellets. A closed-loop cooling circuit solidifies the pellets immediately upon cutting, giving them a consistent size and smooth finish. These pellets become industrial-grade feedstock, ready for use in producing packaging, synthetic fibers, or even molded into brand-new bottles. From these recycled pellets, the factory moves into the preformed molding phase. The material is checked for consistency and then sent into an injection molding unit, where it is heated to roughly 480 degrees Fahrenheit. In this softened state, the plastic is injected into a steel mold, forming a thick-walled tube with a threaded opening already designed to fit a bottle cap. Each preform is engineered to endure both elevated temperatures and internal pressure, ensuring stability during handling. Its compact geometry makes storage and transportation highly efficient, allowing manufacturers to deliver them to bottling plants located near consumer regions. In the following phase, the preforms are heated until they reach a pliable, rubber-like condition, then transferred into a stretch blow molding machine. High-pressure compressed air is injected through the neck, causing the softened plastic to expand and press firmly against the interior surface of a metal mold shaped like the final bottle. It is visible how a preform only 4 to 5 inches tall stretches to nearly 4 or 5 times its original dimensions in the blink of an eye. Once the blow molding step is completed, each automated line is capable of producing thousands of bottles in mere seconds with an almost zero defect rate. Laser-based inspection systems constantly monitor wall thickness, symmetry, and transparency to maintain consistent quality. Beyond typical bottle designs, the machinery can adjust volume, contour details, and label positioning to match each brand's specifications. Everything only gets more complicated as the bottle heads for final stabilization. After leaving the mold, the bottle body is still extremely hot and prone to distortion, so the production line immediately guides it into a rapid cooling chamber that uses either chilled air or circulating water. This stage lasts only a few seconds, yet it is sufficient to stabilize the structure and lock the shape in place. In some advanced facilities, the heat released from the freshly formed bottles is captured and reused to warm the cooling water, greatly lowering overall energy usage. Once the plastic has completely solidified, the bottle attains the necessary mechanical strength to endure internal pressure during filling and transport. Before leaving the production facility, every plastic bottle must pass through rigorous quality checks where optical sensors and high-resolution cameras identify even the tiniest flaws. Systems detect microcracks, trapped air bubbles, or dimensional inconsistencies. Certain samples are selected for mechanical evaluations such as tensile strength, compression, and impact resistance to confirm overall durability. For bottles designated for food applications, additional chemical screening ensures that no harmful residues are present. Thus, only after satisfying all requirements are the bottles grouped together, stacked onto pallets, and shrink-wrapped for protection. Automated palletizing robots arrange thousands of units with inch-level accuracy, tagging each batch with a unique traceability identifier. From the central distribution area, the finished goods are shipped to beverage factories, supermarkets, or retail locations. The material is ready to re-enter the economy, completing the transformation from discarded waste to a valuable resource. Countless fragments of drifting debris complete their transformation into a valuable industrial resource. What was once waste polluting the currents now enters a completely new material cycle. One can notice how the chaotic mix has been collected, cleaned, and processed into uniform raw material ready for modern manufacturing. At first glance, this reclamation seems straightforward, but in reality, it requires a complex chain of technological stages. Why is such elaborate purification and reforming necessary? The material travels a long path from the sea to the factory. This rigorous processing ensures that the renewed resources possess the structural integrity required to power sophisticated production lines alongside virgin materials. The journey from drifting trash to a stable product concludes here, but this is just the beginning for the material itself. It is visible how the recycled granules wait to be molded into new forms, validating the innovation behind this recovery method. The cycle closes, turning environmental hazards into essential assets. Thus, the plastic is reborn, ready to serve a new purpose without haste.